Okay, so I think let's get started. So fluid systems play an important role in our everyday life. You can find it in the braking circuits of your car. You can find the fluid circuits like you have big like transport pipes which is used to transport water and fuel, and you also have the ventilation system in your houses. So you can find fluid systems almost everywhere. Hence, it is pretty obvious that you would need to design and do analysis on your fluid circuits, as it is an integral part of various engineering projects. Today, we will have a look at how you can design and analyze your fluid circuits using Wolfram System Modeler. So hi everyone, I am Ankit from Wolfram MathCo. I'm an applications engineer. Uh, so let's get started. For this presentation, I'll be using the Modelica Fluid library, which will be supporting from version 13 of System Modeler. So today we will start by modeling this classical tank example, which you can see in the figure here. Here we have a fluid source, and then we have a pump, and using this pump, the fluid is pumped through the fluid source, through a pipe to a tank here. And then we have another valve through which fluid is then transferred from this tank to the auxiliary tank. Let's start modeling this simple classical tank example in System Modeler. So let me open it. So for people who are new to System Modeler, this interface is called Model Center, and this is where we usually model in System Modeler. So here, as you can see, I have prepared the model, some parts of the model beforehand, so that we save some time. So let's get started here. So here, as you can see, we have various components, and these components I have used from the Modelica Fluid library. This is a new library which will be shipping, or which will be supporting from version 13. And as you can see, inside this fluid library, we have various components. One component that we have used here is the system component, and this component is used to define the global properties of the model. For instance, you can see here it's used to define the pressure, the temperature, and the gravitational acceleration in the model. Also, in the fluid component, we have different sub-libraries like the vessels, and inside the vessels, we have components like closed volume open tank. We have used two instances of open tank in our model, the tank and auxiliary tank. And similarly, you have the other components like pipes, machines, valves, and so on. You might recollect that from the model which I had shown before, the only component that we are missing in this example is the valve component. And that valve component can be found in the valves library here. So if I open the valves library, you can see there is a list of various types of valves. We have valves like valve for incompressible flow, valve where vaporization can take place, valve with compressible flow, and so on. For this example, let's take the valve with incompressible flow. I will just drag it to my interface here, and I will give it a suitable name. So let me just call it valve, click OK. Now, before I start using this component, the first thing that would come to your mind is what does this component do and how is it modeled? So you'd like to know more about this component. In order to do that, we can start by looking at its documentation. And in order to do that, you can right click and go to class documentation, or just select the component and press F1. When you do that, you will be brought to this documentation page, as you can see here. And it starts with some description about the valve, like it says the valve model is based on IEC standard 534 and so on. And it also says that this model inherits the parameters from the partial valve component. So if I click there, it takes me to this documentation of the partial valve, based on which this valve component is modeled. And in this component, you can see the detailed description of the various parameters of this component. The most important parameter that you should be interested is the valve characteristics. And here it shows that in this model, you can define the different types of valve characteristics, like you can have a linear change in the valve characteristics, or you can have a quadratic change, or you can even define custom valve characteristics for this component. One thing to note is, you see, the value changes from 0 to 1. So we have to define a value from 0 to 1 in order to completely close or completely open this valve. So, uh, so as you can see, this valve is based on this partial valve, which has a lot of parameters. And the list of parameters, you can, of course, also find it here as well. So you can see it has the different parameters like the area, the flow coefficient, and so on. And also you can define the nominal mass flow rate or the nominal pressure drop across this component. But the interesting thing, whenever you start using a new component, is you want to know how the component needs to be used. And in order to do that, one of the important resources like the used in examples section. And here it lists the different examples where this component has been used. Let's open the heating system example. If I open this example here, you can see this valve is fed with a step input handle, as you can see here. So let's copy this component and use it in our model. So I will go back to our model and paste the component here. I will give it a suitable name. Let's say valve opening. Click OK. Now let's start connecting these components. So in order to connect it, I will use the connection line tool, and I will connect this valve to my auxiliary tank here, and I'll click OK. And here I can connect to my main tank. And here you can see it is asking me which port I want to connect. In this case, I will click port 2. And that is because this tank has 2 ports, and one port is connected to the main inlet line, and the second port we would want to connect with our auxiliary tank. So I've selected port 2 here. Similarly, I can connect my valve opening to my valve component here. Now our model is quite ready, not complete yet, but it's almost done. One more thing, when you one of the most common thing that you do when you create a model is you would like to use some sensors so that you can access some critical properties of the system. In this case, for instance, let's say you want to access the pressure values at the inlet and at the outlet of the valve. So I will create 2 pressure components and quickly give it a suitable name. Like I will call it pressure inlet, and the other one I will call it pressure outlet. And like the other components, I will use the connection line tool and connect my components. So our model is almost ready. The last thing that we need to do in order to start simulating this model is to verify or give it suitable parameters. For instance, if I click the valve opening, it says that initially it starts with 0.1, and after some time, after a time of 2000 seconds, it goes to 0.9. In this experiment, I will just use a start time of, let's say, 3 seconds. Then I will click valve. So when I click the valve component, you can see in the generals tab, I've been asked to feed in all the parameters. And most of the parameters have already been given a suitable value depending on the model, or they've been given suitable start values. So you don't need to think about that. There are 3 things that you need to specify in this component. The most important thing is the valve, is the medium. So you need to define which fluid is passing through this component, and in this Modelica Fluid library, you have access to hundreds of different predefined mediums that you can make use of. So you can see here you have properties for ideal gases And if you have properties, you have properties for simple flue gases, moist air, and so on. In this case, I will use something called medium here. And this medium is a parameter that I have created at the top level or at the high. This parameter is something which I have defined in my model before, and I'm just referring back to this parameter name there. So here I have defined my medium as the medium, which is in the top level. And two more things I have to define here. I have to define the nominal pressure drop. Let's say, let's set it to 0.1 bar, the nominal pressure drop across the valve. And also what is the maximum nominal mass flow rate allowed to pass through this valve. Let's take it as 10 kg per second for now. Now we have set all the parameters for the valve. We have set for the valve opening. For the pressure inlet as well, we need to specify the medium. So I select it and specify and write it as medium. For the pressure outlet, I select it and write it as medium. So now our model is ready and we can go ahead and simulate this model. In order to do that, I will click this play button on the top. And for the new users, this brings us to Simulation Center, where you can visualize the results of your model. You can visualize the results as plots, or you can, if your model has animations, you can visualize the results as animations as well. So here, let's plot the things which we want to check. We would like to check the level of tank in the auxiliary tank here. And we would also like to compare it with the level of fluid in the main tank. So I will select here. And let's create another subplot and let's plot the pressure at the inlet and the pressure out the outlet. And for reference, I will also plot my valve opening as a third subplot. So as you can see here, when the valve is closed in the top plot, the level of the liquid or the fluid in my auxiliary tank is almost 0. And as I switch on my valve, the level of the fluid in the auxiliary tank goes up. And also there is a small dip. If you observe carefully, there's a small dip in the level of fluid in the main tank. Another interesting thing that you might also observe is the pressure curve here. So here you can see at the inlet pressure, as the level of liquid in the main tank increases because of the gravitational head, the pressure at the inlet increases. And on the other side of the valve, that is toward the outlet side, as the height of the liquid in the auxiliary tank is increasing, similarly, correspondingly, the pressure at the outlet of this valve is also increasing. Right. I will just save this, add this model to my plots. I will just store it, store this results in my model, and I will call it results, and I will store it as a default plot. And also for reference, I will give it a name. Let's say water, because I've used water for this medium, for this model, and I will pin it so that I can compare it with my other experiments. So I have pinned this and given it a suitable name called water. Now let me get back to a model center. So as I said, in this the fluid library, you have access to like hundreds of different mediums. And the advantage of that is you can quickly select any of this medium and quickly iterate through various designs. So for instance, let me just change the medium to some isothermo 650 oil, and let me simulate this model. Now we can just compare like what would happen if we change between a water and oil, like how would the system change? And for now, let me just give it a name. Let me say oil and click OK. Then I will select water and pull my saved results here. So here you can see the level of the liquid in both the instances, in both the auxiliary tank and tank has changed. But here, one interesting thing you might observe that why is the pressure at both the inlet and outlet the same if I have two different liquids with two different densities? The reason is the pump that I have chosen is a pump with ideal mass flow rates. The mass flow rate is constant, so that's why the pressure is the same, but the height of the fluid in both the scenarios has changed. Right. So so far we created a simple example, and we saw how we can quickly iterate through various mediums. The next thing that you might be wondering is, for most of the fluid applications, one important thing is you would like to uh, model, or you'd like to have thermal interactions in your model. And then the question would be, can you do that? And the answer is yes. So here I have created a simple example of a pipe network which has like 11 pipe segments, and it has 3 different valves. And as you can see, I'm supplying heat to the pipe 8 here. The interesting thing or the results which we would like to see is, how would the temperature of the fluid inside this pipe 8 change, and how would the temperature at the outlet change? Like how would this temperature affect my temperature at the outlet? And if I go down here, you can see as I start heating my pipe 8, here is a plot of the outlet at pipe 8 and pipe 11. So here you can see in pipe 8, as I start heating, my temperature increases, and this increase in temperature is then propagated to my pipe 11 outlet. But one interesting thing I wanted to point out here is, you see, we have this valve, we have the valve opening one, which is closed at 50 seconds. So the valve opening one refers to this valve over here, and we are closing it after 50 seconds. And what that is doing is, in pipe 8, the initial mass flow rate was 0.5 kg per second. But now when I close this valve, my mass flow rate is minus 0.8, or in the negative direction. So that means that I am able to model the reverse flows in my pipes as well. So that is another advantage when using this components, that you don't need to define the directionality of the pipes. It automatically determines the direction of the flow from the boundary conditions. Right. The next thing which we would like to check, or which you would like to ask is, okay, I can do thermal interaction, but can I also deal with fluids which have multiple phases? And the answer is yes. You can use the fluid library to model phase change. For instance, here's an example of a drum boiler. So drum boilers are used in power industries, where you put in a feed water, and that feed water is heated and converted into steam. And that steam is then used in the turbines to generate electricity and so on. But here in this example, I have a simple pump which puts feed water to the boiler. I heat it through the furnace, and the output, the steam output which is coming out, I'm storing it in a sink in this case. And I also have a controller setup to maintain the level of liquid inside my boiler. As you can see here, I have the plot results from this model. And the most interesting plot is the first plot here. And here you can see at the start, we had some amount of vapor, which is marked by the orange line, and some volume of liquid marked by the blue line here. And as you can see, initially when uh, initially uh, when the heat is gradually being added, the amount of steam and vapor remains the same. But we are eventually taking out the steam from the steam valve here. So you can see the steam flow rate here, and it's going out from the system. And when the steam goes out of the system, water is then converted to steam at around 20 minutes, as you can see here. And once water is converted to steam, the level of water in the boiler drops, and the controller starts feeding in more feed water, as you can see with the bump here. And then after some time, the mass flow rate of water to this boiler and the mass flow rate of steam going out of the boiler is constant. And then we have reached a steady state system. So in this example, you saw that you can model uh, systems with change in phases. One more question it might come to your mind, that okay, now I can model multiple phases, but can I also model systems which have different substances? Like can I model air which has nitrogen, oxygen, carbon dioxide, those kind of elements in it? And the answer is yes. You can. We have using the fluid library, you can use media that have mixture of different substances. For instance, in this example here, I have used uh, a room model where we are controlling the carbon dioxide level, because in a room, to have a good indoor air quality, the carbon dioxide level should be less than 1000 ppm, and if it goes more than 1000 ppm, the indoor air quality is deteriorated. So here I have this volume which resembles a room, and I have some people which contributes towards carbon dioxide through respiration, and then I have a fresh air circuit which pushes, or which provides fresh air to this room, and then I have a duct through which the stale air or the mixed air goes out from the system. And then we have a control system that monitors the carbon dioxide level in this fresh air supply, and then it tries to maintain the carbon dioxide level at a fixed level. So here in this plot, you can see initially when the number of people, there are no people in the room, the carbon dioxide is set, there is no action taken, it is set at 1000 ppm, and there is no fresh air supply to the room. But as soon as we have people inside the room, the amount of carbon dioxide entering the room increases, and that leads to this jump in the amount of carbon dioxide level. And in order to balance this, our control circuit pushes in more fresh air, and then we try to, and then it tries to maintain or get the carbon dioxide level back to the original, to the desired level. There is it uses fresh air because in fresh air the level of carbon dioxide is low, which is around 300 ppm. So it tries to average out the amount of carbon dioxide in the room. And if I zoom in into a particular section, you see as soon as the number of people the number of people increases, carbon dioxide entry inlet increases, and then the amount of carbon dioxide shoots up, and our control system responds, and it gives a more fresh air supply to the room. Right. So in this presentation, I showed you some key advantages of the Modelica Fluid library that we will be supporting completely from version 13 of System Modeler. So it has some key advantages, like you can model thermal interactions, you can model compressible media, you can use compressible media in this using this library. Also, you can model single substances, like you can just model water, or you can model systems with multiple phases like water and steam, and also systems with a mixture of substances like moist air, which has carbon dioxide, nitrogen, oxygen, water, and so on. So with this, I thank you all for attending this presentation, and now let's open the floor for some Q&A. Right. So let me first check if I have any questions in my chat. Right, I don't have a question in the Zoom chat, so let's me go to the Pathable. So what is the best way to set a component up for others? I would like for the manufacturer's model and pre-populate the parameters. Ideally, it would be nice to have a drop-down of models. So the best way for a model is to create your own library. So this is a question by Glenn, and he's asking what is the best way to set up components for others. One way is, let me get back to System Modeler. One way is you can create your own library. Like I created this fluid models library for this session. So you can create such libraries, and you can then pre-populate those models with the right parameter data, which your customers can then use it. Can these models interact with real life system? Yes, of course. So the thing is, we have we have a library called Model Plug library, through which you can connect your Arduinos. So you can connect your sensor to the Arduinos and feed inputs to this models. That is one way. We also have other libraries which are more industrial in nature, like we have OPC Classic and OPC UA. So using those libraries, you can get inputs from your OPC servers, and then you can add it to your model as well. So you can, yes, you can integrate your model with real life or real world data. Right. What were the steps in the Zoom? Close to 9 hours. Okay, so let me get back to my model here. Yeah, because of the time constraint, I just went fast in it. So there's a question by Harold that what was the time which I zoomed in this figure. So here I zoomed into into this section, so which corresponds to like 8.9 to around 9.25. So it's around 9 hours. So I'm zooming it into this particular section here. Right. Right. So what are the corresponding PDEs and ODEs in Wolfram language? Unfortunately, I don't. I think it's ND-solve is, I think, could be corresponding ODE to that, but I'm not sure about it. And then you can actually join our system modeling office hours, which is just after this session, where we have other developers from the Wolfram system modeler team joining in, and they will be better in responding to that specific question. Okay, how are the time steps chosen? So in this, okay, so let me open up the carbon dioxide model here. So here, if I go to the experiment setup, I see I have this Dassault solver selected for this for the drum boiler example, and this Dassault solver, like it's an adaptive solver. So based on the based on the events, it tries to adopt or adapt the step size. So yeah, but you also have option to choose between several other solvers. You can use CVODs, or if you are interested in fixed step, then you can use explicit Euler or Runge-Kutta method as well. So you can actually switch and iterate between various solvers. Right. Yes. Is this only for 1D problems? This is a question by Yuzo, and yes, uh, this fluid library is mainly for 1D fluid thermal models. So yes, this is mostly for 1D problems. Yep. What thermodynamic models are considered in modeling the water stream system for the boiler problem? So for the boiler problem, if I so this boiler example is taken from a paper which is titled Online Optimization of Drum Boiler Setup, and it has complete description of how this drum boiler is modeled. So those theoretical details, you can find it by referring to this paper. I will just also put it in the chat later on. I think you can export the equations from system modeler to Wolfram language. Yes, you can. Once you have created your model, you can use Mathematica to extract system equations from your model. And once you have extracted those system equations, then you can do post-processing analysis on that. So that's possible, yes. Right. Okay then, so I think our time is up. But for all of you who are interested and have more questions, you are welcome to join the system modeling office hours that we'll be having right after this session, where we can take further questions. Anyways, thanks a lot everyone for tuning in. And if you have any questions, just after this session, also you can put it in the chat and I will respond to it once I get some time. Okay, thank you.